Okay, so I'm going to do something kind of fun. What kind of fun? So, in classical mechanics, we have Newtonian physics, and then we have Lagrangian mechanics, and we have the Hamiltonian. So, what I want to do is to solve a problem three different ways: Newtonian, Lagrangian, Hamiltonian. And then we can see how they compare and talk about what's good and what's bad and when you'd use each one. Okay, so let's just get right to it. Let me turn this camera off because you can't see me if I'm writing. Okay, so let me move this real quick. Oops, that's in the way. Okay, so the problem I want to solve is this block sliding down a frictionless plane. And so it's a block of mass m. The plane is inclined at an angle theta, and I want to find the equation of motion three different ways. So the first way I'm going to use, let me just talk about these three ways, is Newtonian mechanics. So this is what you learn in your introductory physics class. This says that if you have all the forces and you know all the forces acting on an object, that's equal to the mass times the acceleration. Of course, you could also write this as F net equals dp dt. That's essentially the same thing in most cases. In some cases, this is better. But let's just say it like this. In Lagrangian mechanics, we define the Lagrangian as the kinetic energy T minus the potential energy U. And then it turns out that the real motion in the real world is such that the world path minimizes the Lagrangian. And so now you have a variational principle where you're trying to find the function that minimizes an integral. And so to solve that, use the Euler-Lagrange equations. So using the Euler-Lagrange equations, we get this, the partial of L with respect to Qi. So Qi is any variable that we choose to describe the system. And we can have more than one of them. So we have Q1, Q2, whatever. Okay. And then this is Qi dot. Qi dot is the derivative of Qi with respect to t. So we use the dot notation because it gets less cumbersome and it makes us look cool. That's the end. So if I solve this equation, then I can get a differential equation for the equation of motion. Now finally we have the Hamiltonian. The Hamiltonian looks kind of weird, okay? And we'll talk about why you would use this, but when we get to it. Because you can solve the Hamiltonian based on the Lagrangian. So you're thinking, why would I even do the Hamiltonian? I got to do the Lagrangian first. Well, you don't use Euler-Lagrange equations. You just got to find the Lagrangian. And so from that, I add up all the momentums, generalized momentums, times the velocities minus the Lagrangian to get the Hamiltonian. And then I have two equations. The velocity Qi dot is equal to the derivative of the Hamiltonian with respect to the momentum, and then the momentum is the derivative, the momentum dot, the derivative of the momentum is the negative, the partial of the Hamiltonian with respect to Qi. So we have these two equations. Okay, so let me just go ahead and say, the Hamiltonian, well, let's talk about that as we solve them. So let's solve this problem first with Newtonian mechanics, and then we'll do Lagrangian, and I'll talk about each of those as we get to them. So let's do Newtonian mechanics. This actually isn't a trivial problem in Newtonian mechanics unless you use a small trick. So if I start off in Newtonian mechanics, I want to know what forces are acting on that object. So here I should have not drawn the mass. I have the downward gravitational force, mg, and then I have this contact force between the surface and the block. And those are the two forces acting on it. So I could say F net equals N plus mg equals ma. And that's a vector equation, right? Because, yes, mg is in the negative y direction, but still this is the sum of all the forces, so you still have to add them up like that. Now, the problem here is with the normal force. This is a contact force that pushes as hard as it needs to on this block to prevent it from going through the surface. You don't have an equation for that, okay? So the trick here that you probably could guess is to pick a coordinate system where I don't care about the normal force. If I pick this as my x-axis and this as my y-axis, then I know the motion of this mass it's constrained to move in just the x direction. So that I can write this. F net y, the y forces, is going to be equal to 0, because that's mass times acceleration in the y direction. And it doesn't accelerate in the y direction. So I don't even care about that. I want to find the acceleration. I don't really care about the y. If the y acceleration is 0, I'm done, right? And I've set it equal to 0. I didn't solve for that. I just said it has to be equal to 0. You see the difference? So we did cheat. Okay. We used the constraint of the system to say, I know that that's true, instead of using the force to find the acceleration. Okay, but now I can do the same thing in the x direction. F net x equals, let's write this as mgx equals max. So if I draw my axis like this, there's my gravitational force. If that angle is theta, that angle is theta. So now I have the y component and the x component. And so if this is mg magnitude, the x component would be mg sine theta. So I get mg sine theta equals max. So the masses cancel and I get ax. And I'm going to write this as x double dot because we're cool, right? This is classical mechanics. We can write that. This says that the acceleration is the second derivative of the position, and that's equal to g sine theta. Okay, so really we're done right here, but I'm going to finish anyway. So let's just say, how would I solve for x as a function of time? Well, I can integrate both sides with respect to time. So I get this. And this stuff's all constant, okay? And the integral of x double dot with respect to time gives me x dot. And then this is going to give me g sine theta t plus a constant. So the constant is at t equals 0, x dot should be 0. So this is going to be plus x dot 0. Now I can integrate again one more time. And this side I get x. Here I get 1/2 g sine theta t squared. This one is going to have a t plus x0 dot t, and then I have to again evaluate it at t equals 0, so say plus x0. And there's my equation of motion for a block sliding down a plane. And we only cheated a little bit, right? But that's Newtonian mechanics. Normally, Newtonian mechanics works the best if I can calculate all these forces. If I know the values of all those forces or an expression for them, then this is just straightforward. I might get a complicated equation at the end, but to get to this part, it's pretty straightforward. Now, if I have forces of constraint, it can be a little bit more difficult. And I'll show you an example at the end where you would not want to do Newtonian mechanics. Okay. I should show you that now, but I'm not going to. Okay, now let's do the Lagrangian mechanics. So the same problem. So the first thing I want to do is say L equals T minus U. I need to find the Lagrangian. Now, in order, the benefit of the Lagrangian is that we don't have to use Cartesian coordinates. We can use whatever coordinates we want. Now, it may be difficult if you use non-Cartesian coordinates to find the kinetic energy, but you can still do that. So in this case, there's a 1 degree of freedom problem, so I only need one variable. So if I can pick one variable that completely describes the situation, then I'm done. And so let's pick this. That's the distance from the top of the incline to the block is called S. That's my variable. So if I know the value of S, I know where the block is. And so let's call this H, just for simplicity. Now, how do I get the kinetic energy? Well, I know this. T equals 1/2 x dot squared plus y dot squared. And you could probably easily say, well, S is it's just going to be S dot squared. And I'd be okay with that. Okay, but let's just do this the full way. So let's say this is the origin, my xy plane. So the motion, the block is going to have, in terms of this angle is theta, right? That angle is theta. So I can say x equals s cosine theta, y equals h minus s sine theta. Right? Because if I have this is my horizontal component of the distance s, that's my x value because it's whatever that may be. Now for the y value, I start way up here, so I need to subtract the stuff from h. Now I can get x dot. What's the derivative of this? Well, cosine theta is constant, so I get s dot cosine theta. What's the derivative of this? Y dot is going to be equal to the derivative of h, which is constant, minus this, so I get minus s dot sine theta. Now if I square these, x dot squared plus y dot squared, I get x dot squared plus y dot squared equals s dot times cosine squared theta plus sine squared theta squared equals s dot squared. Right, because cosine squared plus sine squared is 1. So the kinetic energy, as we thought, T is 1/2 m s dot squared. Now what about the potential? Again, I can do the potential in terms of, I could say this is mgy. That's pretty easy. And well, I already know an expression for y, so it's going to be mg h minus s sine theta. So that means L is going to be 1/2 m s dot squared minus the potential. So it's going to be minus mgh plus mgs sine theta. So I factored this out, and I multiplied the negative end through that. Is that okay? That's okay. We're going to use that in the next part too, in the Hamiltonian. So I put a box around it. Once you put a box around it, that's it. You're done. Okay. Okay, so now I need to do the Euler-Lagrange equation. So I need to take the partial of L with respect to my variable s. So the partial of L with respect to s, there's no s right here. There's an s dot. There's no s right there. Here I have one s, right? So I have mgs sine theta. That's the only thing that depends on s. So when I take the partial derivative of that, I just get mg sine theta. Now let's take the partial with respect to s dot. And so what has an s dot in it? It's just this term. So I use the power rule, and I bring the 2 down. I have 2 over 2 m s dot. So I have m s dot. Now I need to take the derivative of this with respect to time. The derivative with respect to time is going to be equal to, well, m's constant. So I just get the derivative of s dot with respect to time, so I get m s double dot. Now I can set this equal to that. M s double dot equals mg sine theta. The masses cancel, and I get s double dot equals g sine theta. And so that's the same equation as before, right? I had it in terms of x. I could integrate twice. I could find the same thing. Remember, I had my x-axis in the same direction. So I get the same thing. There's no point in solving that equation all the way, integrating twice. It's easy to do, but we already did it. So I'm not going to do that. Okay. So I solved that problem. I got the differential equation. Getting the differential equation is the physics. Solving the differential equation is the math, which you may be able to do it explicitly. You may have to do it in Python and break it up into pieces, whatever works. Okay, so now the Hamiltonian. So again, let's go back over here. I can use that same variable s. Again, I don't have to use actual coordinates in the Hamiltonian. So I'm going to use this same thing. So I did that with the Lagrangian. That's an arrow. So I need to first find the Hamiltonian. So to do that, I need the Lagrangian. So I have this 1/2 m s dot squared minus mgh plus mg sine theta. We already had that from before. So now h is going to be I'll write it out, the sum of pi qi dot minus L. Well, I need to find pi, right? I need to find the momentum. So P is just going to be m s dot, right? It's mass times velocity. In this case, I can do that. There's another way you can actually do this to make sure that's true, because sometimes it's not. If you think about cylindrical coordinates and spherical coordinates and stuff, it doesn't always work, but here it works. So I can write, there's only one variable, so I get h equals p ms dot. This is going to be s dot. Now I need to subtract off the Lagrangian, so it's going to be minus 1/2 ms dot squared plus mgh minus mg sine theta. So here I have ms dot squared minus 1/2 ms dot squared, so I get 1/2 ms dot squared. And then I get plus mgh minus mg sine theta. Now you'll notice here, that's t and that's u. So this is equal to t plus u, which is the energy. So in this case, the Hamiltonian is equal to the energy, but it's not always equal to the energy. Okay, so you gotta be careful about that. And also in quantum mechanics, we use a Hamiltonian, but we use it as an operator, so it's a little bit different. But that is the same Hamiltonian, just so you know. But I have the Hamiltonian. Now I can use the two Hamiltonian equations. So the first one is going to say that S dot is the partial of H with respect to P. Okay, so here's my H. Oh, no, that I can't do that yet. I need to get this in terms of P's first, right? So here I have an S dot. So S dot is P over M. So if I put that in up here, I get H equals, I get P squared over M squared. So this is going to be P squared over 2m, one of the m's cancels. And then I get plus mgh minus mg sine theta. Now I can do this. S dot equals the partial of h with respect to p. So if I take the partial, there's only one p in here and it's this, so I get power rule, the 2 comes down, I get 2 over 2 p over m. So that's equal to S dot. I'm going to put a box around that. Now I can do my other one, P dot equals negative partial of H with respect to S. And so now where does S come in here? I have, oh, this is an S, mg, S, 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 S. And that's going to be minus 2 points for your errors. Okay, sorry, that was my fault, but I caught it. Yep. Okay, the problem, my mistake, I'll tell you right now, is saying MGSS ein theta, right? I had two S's right next to each other. So the partial of H with respect to S is just going to be, the only S that shows up is here, so I get MG negative, MG sine theta, but there's a negative sign, so I get MG sine theta equals P dot. Okay, here's an important point that's the difference between Lagrangian and Hamiltonian. I have a solution. I have two first-order differential equations. And with the Lagrangian, I had one second-order differential equation. So that's the difference, okay? But let's go ahead and solve for S double dot. So I'm going to take the derivative of both sides right here. I get S double dot, I'm running out of room. Never run out of room. S double dot equals P dot over M. And then I already know an expression for P dot right here. So this is going to be mg sine theta over M equals g sine theta equals S double dot. So I get the same thing. Okay, I get the same differential equation in all three cases. And so in this case, you can do it any way you want. Okay, so let's think about some problems and how you would solve them and which method you would use. I'll go ahead and tell you, for the Hamiltonian, you don't see an advantage. Okay, you don't see an advantage between Lagrangian and Newtonian mechanics and the Hamiltonian, but that is what we use in quantum mechanics. It is used in statistical mechanics for large systems of particles. It turns out to work the best. Okay, so but at this point, it seems the same as Lagrangian. Okay, so let's think about this problem. So here's a object orbiting a planet. So what would you do to would you use to find the equations of motion here? Well, you could use Newtonian mechanics. Let's just write F net equals ma, and then L equals t minus u, and I'll just leave that, because yeah, I'll go ahead and write that one. H equals what was it? Qi it's Pi Qi dot minus L. Okay, so which one of those three would you use? In this case, I can explicitly calculate the gravitational force. It's an equation. I know the vector force at any particular location, so I can use this. Okay, the math gets a little tricky unless you use some tricks or do a numerical calculation. I could use this, right? Because again, I can calculate t minus u and it works out just fine. I can calculate t, I can calculate u, done. And then so again, the Hamiltonian works. All these work fine. We saw for the block on the plane, they all work fine. What about this? A pendulum. So in this case, this is not easy, right? Because what's the force? I have the gravitational force pulling down, and then I have the tension up. Now, the tension changes direction, and it changes magnitude, right? Because this tension does whatever it needs to do to make this move in a circle. So as this thing speeds up and moves in a circle with a greater speed, the tension increases. So it's not trivial. You can find a magnitude, an expression for the tension using energy, but other than that, you can't. Now, the other option is to cheat and to use polar coordinates. In polar coordinates, the only variable that changes is theta. But then I have to write the acceleration in terms of polar coordinates, which I'd made a video of down below. You can see that. So you can use Newtonian mechanics, but it's not trivial. Okay, and that's one of the things. I don't really like this problem in the introductory physics textbooks unless you're just talking about energy, because it's a pretty hard problem. For the Lagrangian and the Hamiltonian, this is a nice problem, right? Because I can pick theta as my variable. It doesn't matter that that theta is not a Cartesian coordinate. I may have a little trouble finding the kinetic energy, but I can do that. Okay, and it's not so bad. And so you can do it either way, but here, this one's better. What about this? This is a double pendulum. A double pendulum is super hard, right? Because now I have this two constraint forces, T1 and T2. This force doesn't just have to do with the motion of that mass, but the motion of that one, right? Because this one pulls on this mass too, so this has to compensate for the motion of that. This is pretty much, I don't know how you would do this in Newtonian mechanics. You couldn't calculate the forces. You couldn't cheat to find the forces of constraint. However, with Lagrangian, I have two variables, right? And even though this variable depends on that one, that doesn't matter. I can still do it. I can write down the Lagrangian, I get two variables, and I can do it. So that's a case where you can do it like that. So the Lagrangian wins in places where you have strange constraints. And here's another Lagrangian motion, a bead sliding down a weird wire, right? How would you find the force of constraint? That's pretty hard. But if I just parameterize this as the position along the wire, it's not so bad as long as I have a function for the wire. So forces of constraint, constrained problems, Lagrangian and Hamiltonian. If you know the exact forces, this one. Now, where does this one not work very well? Here's another example. One more example. Oh, we did that one already. But what if there's a frictional force? A frictional force isn't really an equation of a constraint force, right? It decreases the energy of the system. So the Lagrangian doesn't really, you can make it work. There's some tricks to make it work, but it's not easy. The Lagrangian wants it to be a constant energy situation. And so if you're losing energy, then it's much more difficult. It's probably easier to deal with losses of energy in the Hamiltonian, but for Lagrangian, this one I would definitely do Newtonian mechanics, but still you got to make a trick, right? Because you don't actually know this normal force, the force of constraint. You have to find a trick to solve for it. Okay, but those are the three different ways to solve mechanics problems. I have nothing else to say, so I'll talk to you guys later.